right, so thanks everyone for joining us. My name's Ayman Amir and I'm the Toronto Reactor Program Manager. I'd love to know where in the world you're all joining from. But Jaya is based in Toronto as well, and we're really excited that you're joining us today. So this live stream, it's going to be about 45 minutes and we'll leave the last 10, 15, 20 minutes or so for any questions that you might have. So our speaker today is Jaya Matthew. She's a senior data scientist at Microsoft and part of the Azure Global AI team. Her work focuses on the deployment of AI and ML solutions to solve business problems for customers in many different domains. Before joining Microsoft, she used to work with Nokia, HP on various analytics and machine learning use cases. She has an undergrad and graduate degree from University of Texas at Austin in maths and statistics. So thanks so much for joining us, Jaya. We'd love to learn more. This is an awesome topic and thank you for doing this.
Thanks, Ayman, for the introduction. So hopefully most of our audience can dial in today. I heard there were some issues. Okay, so let's get started with our topic. So it's kind of a long title. How do you get the most out of your IoT data? So we'll get started with some of the basics of any kind of data collection, predictive maintenance, and how to kind of use your data to build either a traditional or a deep learning model. So let's go to the next slide. Oops. Okay, yeah, there we go. So this is a quick outline of my talk. So we'll first get started with setting the context for what a connected factory is. So that's how a lot of data gets collected. Then we'll define what is manufacturing maintenance. Then to get a basic understanding of the rest of the talk, it's important to define what predictive maintenance is. What is it? Why do we need it? What are the different types of maintenance models? Then we'll actually get into how to build a predictive maintenance solution. So we'll go through the basic approach. We will actually work with some simulated sample data, so you kind of get a feel for what feature engineering looks like. Then we'll do some basic modeling. How do you evaluate models? Then we'll also do a comparison of traditional models where you actually manually do all the feature engineering versus deep learning modeling techniques. So one of the deep learning approaches that's suitable for time series data that you get from connected factories is something known as LSTM, long short-term memory network. To wrap up, I'll actually give you some suggestions on our Python code and where you can kind of get some starter code for you to kind of use for your data set. I should ideally have about 10 to 15 minutes towards the end for any questions that any of the audience might have. So would request all of you to keep the questions to the end of the talk. Okay, so let's get started with what is a connected factory. Okay, if we actually think of the various phases in the Industrial Revolution, in the late 18th century was essentially the first Industrial Revolution where we had steam power come in and it kind of made a lot of mechanical production possible. Then we essentially, in the beginning of the 20th century, started the second Industrial Revolution where electric energy made mass production possible in factories. In the beginning of the 1970s, that's just about 50 years ago, was essentially the third Industrial Revolution where IT and computer technology allowed for a lot more manufacturing automation. And now since the 21st century, that's just about the last 15-20 years, you have a lot of Internet of Things making network manufacturing possible. So that's essentially coined as the fourth Industrial Revolution. So our focus would be on Internet of Things, which is the fourth Industrial Revolution. So what is this Internet of Things? What can it do? So essentially, if you think of it, it can enhance the customer experience, it can help you innovate faster, and it can also transform operations. So about 83% of the manufacturers that were surveyed said that selling products as services helped increase their profits. So that's where they kind of thought of, selling add-on services for all the equipment that they sell. Then 40% of industrial manufacturers use digital technologies to monitor products sold to customers. So you might have an RFID tag on some of the products that get sold, or you have an app that pings the server etc. Then 79% of companies use IoT. IoT is Internet of Things, to become more efficient and more responsive to customer needs. 35% of the manufacturers collect and use data generated by smart sensors to enhance manufacturing. So as opposed to actually going and assessing each and every equipment, if you have some smart sensors which sends data periodically back to the server, you can actually remotely monitor the performance. 80% of the manufacturers also expect to improve factory connectivity to transform their operations, and 85% of the manufacturing executives expect human machine-centric environments to become commonplace. I think it's already started to become, but they expect that to accelerate a bit further in the next few years. Okay, so now we do know that with this fourth industrial revolution, there's a lot of data being collected in factories, and all that is collected in some data center, either on premise or in the cloud. But interestingly, most of this IoT data is not currently getting used. So the data is being collected primarily for anomaly detection and quality control charts, but is not being actually used for optimization or prediction, which is where the maximum value of the data actually exists. Okay, so now that we know what data gets collected, let's actually define what is manufacturing maintenance. So manufacturing maintenance, there are a couple of strategies. Essentially, you're trying to make some strategic impact of predictive maintenance, where you're trying to improve the overall equipment effectiveness for mission critical assets where failure patterns are discernible, or you're trying to make responsiveness to kind of prevent any equipment shutdown. So you want to minimize production downtime and associated variability for monitored assets that exhibit some sort of failure patterns ahead of the failure actually. So now why would anyone want to do manufacturing maintenance? Essentially, there are two kind of costs. One is the direct cost and the indirect cost. So let's kind of first look at the direct cost. So typically, maintenance-related costs are approximately 25% of the overall operating cost. So that is about 1/4, which is quite a big amount. So if you can kind of lower that, your margins will improve for your overall operations. They also estimate that 30% of maintenance costs are related to unnecessary expenditure associated with bad planning, overtime, spare parts, inventory, carrying costs, etc. There's also e-loss, which is where variable costs associated with scrap and having to kind of discard the entire line that was produced. So there are also indirect costs. So those are the direct ones that can be measured. Indirect ones are essentially, based on equipment availability and performance. It affects your quality and eventually affects the brand and profit margin. And on-time delivery affects customer satisfaction and lifetime value. So if a customer goes to an ATM machine and the machine's down, well, obviously the customer is not happy with the service rendered to them. So there are indirect costs, and this cannot obviously be quantified at all times, but it does affect the brand. Okay, so now that we know the basics, let's actually get into what is predictive maintenance. Okay, so we've alluded to this in the previous couple of slides, and let's kind of define this in a more formal manner. So why do we need predictive maintenance? So as we stated earlier, unscheduled equipment downtime can be detrimental for any business. So it's essentially very critical to keep field equipment running to maximum utilization and minimize unscheduled downtime. And the goal of predictive maintenance is to extend the useful service life of any equipment and prevent failures. So if you look at the diagram on the right, so essentially predictive maintenance can reduce operational risk, reduce unnecessary time-based maintenance operations, control cost of maintenance, improve overall brand image, lower inventory costs, and discover patterns connected to various maintenance problems. So they have quite a few advantages. That's why a lot of companies are looking at predictive maintenance and how to use their IoT data. Okay, so in terms of predictive maintenance, the business problems can be categorized into three main buckets. So one set of questions is essentially it's trying to answer what is the probability that an equipment will fail soon. So soon would be in the next 1 week, next 1 hour, next 2 months, etc. Then some customers are interested in trying to figure out what is the remaining useful life of an equipment. So that is before your next maintenance request by the service team. And the other set of questions, the third category is what are the causes of the failures and what maintenance actions should be performed to fix these issues. So if they know the cause of a failure ahead of time, maybe they can do something to prevent the failure, which is good for the business. Okay, so in terms of maintenance models, there are 5 types of maintenance models. So the current state that we are in is usually stage 1 or 2, which is the first one is a reactive, which is a traditional break fix. So something breaks and then the customer requests for a fix. So for example, your car breaks down on the highway, you call AAA, and then you say, well, I need my car repaired. So that is the reactive. The equipment stops working and you try and fix it. The second is a scheduled maintenance, which is preventative maintenance, where repairs and services are rendered on a fixed schedule, regardless of the condition of the equipment. So think of this as taking your car for a routine oil and gas, oil and filter change. So that's every 6 months or every year, depending on the make and model of your car. So that is scheduled. So that's usually the current state. So the connected state, with all the data that's being collected, you can actually get into wave 3, which is the condition-based monitoring. So here, what you're actually trying to do is the condition of the equipment is monitored using sensors to indicate the health and indicate maintenance needs via real-time alerts. So you know, due to wear and tear, when the equipment actually needs maintenance, and this varies. So think of a vehicle like your car. Some people drive it every day, some people only drive it on weekends. So a car that's run more often tends to have more wear and tear. Then the wave 4, the one that we are actually going to focus on in this talk, is essentially predictive maintenance. So that's essentially where you're trying to predict the remaining useful life for critical components and to determine the asset health and usage patterns and repair history to improve maintenance planning. And the futuristic is the cognitive, which is intelligent operation, where you kind of want the machine to do autonomous actions to ensure maximum asset utilization and efficiency. So we want to reach a stage where maintenance is automatically scheduled in consideration of the health of the machine. So that's more of the futuristic. So we will focus on part 4. Okay, so you also want to actually align your different failure modes by the maintenance activity. So like I said, the reactive, which is what we all do, is typically you want it to be small items that fail, non-critical, and items that are unlikely to fail. So preventative is you want to do age exploration, acceptance testing. And if we jump into what we are going to look at, which is predictive maintenance, we kind of look at equipment that is subject to wear out, consumable replacement, and failure known patterns. Okay, so now to kind of help consolidate these concepts, let's actually look at some typical scenarios across verticals. So I've actually only listed 4 verticals, which is aerospace, utilities, manufacturing, transportation, and logistics. However, there are many other industries and verticals that you might be aware of, which also use predictive maintenance. So in the aerospace domain, so think of an aircraft, think of a helicopter or anything. So you might be interested in trying to predict what is the likelihood of delay due to some mechanical issues in the aircraft. Or you might be trying to predict when is an aircraft component likely to fail next. So if you can accurately predict this ahead of time, you can prevent delays and disgruntled customers. In terms of utility domain, that is either your power, energy, wind farm, solar farms, etc. You might be interested in trying to predict when is my solar panel or wind turbine going to fail next. Or if you think of an ATM machine that any of our banks have, TD, RBC, so they always want their ATM dispensers to be up and running all the time so that their customers are happy every time they go there. So they might be interested in trying to figure out, is the ATM machine going to dispense the next 5 to 10 notes without a failure, etc. In terms of manufacturing, like we kind of spoke about earlier, you're kind of interested in trying to figure out what is the root cause of a test failure, and will the component pass the next stage of quality testing, or do I need to rework the whole lot of components that was manufactured, etc. In terms of transportation logistics, this is slightly more easier for us to relate to on a day-to-day basis. So think of, most of us work from home these days because of COVID, but when we used to go to offices, we typically are in buildings with a lot of, elevators, and you obviously want the elevators up and running during peak hours, so you don't have to endlessly wait for one single elevator or take the stairs. The other one is in terms of your car or vehicle, you want to know, should I replace the brake discs on my car, or can I wait for an additional month? So maybe I'm a user who doesn't drive my vehicle as much, so maybe my brake discs or pads are not as used, so maybe I can use it for some more time before I go to the service center. Okay, so these are some of the verticals. There are many more verticals, but yeah, I've just given 4 of them in here. Okay, so now that we know the basics, let's actually see how do we get started with this whole thing. So essentially the first thing is you want to start gathering data. So we've noticed a lot of companies have data, but they may not actually have all the relevant data. So it might be a good idea to start gathering data for a single machine if the company doesn't have machine-related operating data, or before they gather for all the machines and then realize they haven't collected the pivotal data needed for the analysis. So in terms of data that needs to be collected, you need data in 5 specific categories. One is the machine operating specification data, which is operational parameters like primary data like spindle speed, flow rate, etc. Then secondary measurements like temperature, pressure, tertiary like energy consumption. And then the manufacturer also might have something like mean time between failures, etc. Then typically, if a machine has been in use for a few years, a few months, you might have actually some maintenance history. So you might want the last 3 to 12 months of records of parts replaced, consumables, labor, events, etc. And a list of historical unplanned and planned maintenance requests for that machine. In terms of maintenance process and execution, you also want the list of tasks, work orders, maintenance resources, parts, inventory, lead time, etc. And then you also should have a process where you kind of schedule and manage planned activity as well as unplanned. In the event of an unplanned, how do you quickly execute? Then you have a bunch of manufacturing KPIs, key performance indicators, which is essentially capacity loss, return on fixed assets, etc. And then you have a bunch of audit related, like what is that level 1, 2, 3, 4, where you have the manual documentation, sensor scatter readings, ERP planning data, etc. Now, in terms of tracking maintenance, so the thing is you need all this in place because there's no point building a model for predicting when an equipment's going to fail if you don't have the entire process in place to kind of plan, schedule, order the spare parts, and have someone go and actually do the repair and maintenance. So for that case, you kind of need to identify the work in terms of number of hours where you have some labor force available to do the repairs and number of work order requests, etc. Then you also need to think about work planning and scheduling. So there's a percentage of scheduled hours over total number of man hours that an employee has, then planned hours downtime versus total hours downtime. So this will kind of give you a bunch of percentages and measurements. So even in terms of work execution, so you might have a team of 10, 12 people to go and look at certain equipment. You also need to know the percentage of work orders within a certain due date, percentage of work orders assigned for rework, and number that's sitting in the backlog. So in terms of maintenance, you also need equipment effectiveness, maintenance cost effectiveness, safety, and environment. So in terms of equipment effectiveness, you want to know about number of unplanned maintenance interventions that actually came down, the breakdown frequency, unscheduled maintenance downtime, availability, number of shutdowns, etc. So in terms of maintenance cost effectiveness, you want to think about maintenance cost over replacement cost, maintenance cost per product unit, etc. So this all helps you quantify how expensive it is to do certain actions based on what the model actually helps you predict. And finally, it's very important to ensure that there are no environmental and safety related incidents within any of these environments when we actually send people for repairs. Okay, so now that we know the basics, let's actually get into the approach. So I would categorize this into a 6-step process so over the next 6 slides, we'll get into each one of these steps in more detail. So the step 1 is to identify your target outcome. Step 2 would be to get an inventory of all possible data sources. And then step 3 is you have all the data, you clean it, you organize it and make it ready to use for your model. Step 4 is you build one or more models, you test and integrate. Step 5 is once the model is acceptable by the business, you want to validate it in a live operational scenario. And then 6 is you want to integrate it into operations. So until and unless you actually integrate it into operations, you're not actually getting the full value of your model. Okay, so like I said, step 1 is to identify the target outcome. So that's where you're trying to determine what outcome you ultimately want to achieve. So assume that the building has something called a servo motor. So you know that the last time the servo motor failed, it cost thousands of dollars and operations were down for days. So you want to prevent that downtime for days. So as a product manager, you might be like, I want to understand how much time each servo motor has before it needs maintenance so that we can prevent unplanned failures. Step 2 would be to get an inventory of all the data sources. So you want to identify all potential sources of data, including the types of data and the amount of data available. So in most cases, you would be actually surprised how data is in different silos throughout the organization. So you might have operating patterns data somewhere, failure logs, sensor data, maintenance logs, performance data. So when you're building the model, you actually want to get all the silo data into some centralized repository so that you can use the goodness from all this data for your modeling process. The third is once you actually have a list of all the data, you want to actually connect all your data sources into a single place and prepare for analysis. It's actually interesting to actually build some Power BI or some visually interactive dashboards where you can actually look at mean, median, and some of the basic statistics. And this also lays the groundwork for a robust predictive maintenance model. Step 4 is where you actually build models. So you might build a couple of models, model A, B, C, and then what is that? Then you kind of see which model actually works better. And in this case, you might say, well, you know what, model B is better than model A, so maybe I'll put that into production. So your goal is to make your model actionable by understanding how much advance notice the maintenance team needs in order to respond. And then many a times you actually say that model B is the best, you put into production, and you might get feedback saying, no, it's not really good. So you need to go back to the drawing board and make changes. Okay, so assuming that I said model B is the best and the business team says, well, it seems to do well with historic data. Now let's try it with the latest data that's coming from the servo motor. So you want to apply that model B to live streaming data and observe how it actually works. And then you have to be willing to refine the approach based on the results from this live validation, because many a times the historic data may not be very good indicator of what's actually happening. And finally, once you have the model, you're happy, you've tested it in a live scenario and you're happy with it, you want to actually integrate it into operations. So many a times what we've noticed is a very good model is built, it's tested, but they don't know how to incorporate it into the entire process of operations. So you want to operationalize the model by adjusting maintenance processes, systems, resources to act in near real time. And so here's where you actually, the model might say, the servo motor is going to fail 3 weeks ahead of the failure. So that's when it gives you enough time to order the replacement part. And then maybe 2 weeks ahead of failure, maybe 1 week ahead of failure, you want to send the repair team to repair the servo motor so that it never fails and you don't have any downtime. Okay, so now it's kind of easier if you see this done with some simulated data. So we will go back into step 4 where we actually build the model. So let's actually think of a more specific use case. So you have a scenario where hourly sensor data from a factory is being collected and the customer has noticed that a lot of components are failing and wants to use the IoT data to build a model to predict these failures. So essentially the goal is to predict component failures. So this is a very simplified scenario. It's more like a toy example where this machine has just 4 components, 1, 2, 3, and 4. And you're trying to address the question, what is the probability that the machine will fail in the near future due to failure of a certain component? So data, like I said, is in different silos. So here you have telemetry data, errors, maintenance, machines, and failure. And the task is essentially, it could be a prediction task, a failure prediction, a maintenance action recommendation, etc. So these are the 5 tables of data that you have. So in the next slide, we look at some sample data so that it's just easier to understand the definition with how the data looks like. So telemetry is essentially time series data, which consists of a bunch of measurements from the machine. So it could be voltage, rotation, pressure, vibration, collected from machines in real time. So typically we will average this data. So maybe some machines have sensors that give the data every minute, every 30 seconds, 5 minutes, 10 minutes, but typically you want to average it so that there isn't too much of noise in the data. Then in terms of error, you have non-breaking errors thrown while the machine is still operational. And you also want to round the error date and time to the closest top of the hour so that every table can be mapped. Maintenance could be scheduled or unscheduled maintenance records. A record is generated if a component is replaced during the scheduled inspection or breakdown. Machine is the static table, which has the model, make of the machine as well as age, depending on the year of manufacture, etc. Failure is what we're trying to predict. So a failure table essentially has a record of component replacements due to failure. So now let's look at how the data looks. So if you look at the telemetry, if you look at the first 4 tables, which is telemetry, errors, failure, and maintenance, you'll see that they all have date time. The date time is actually to the top of the hour, so that it's easy for us to map these tables. Then all these tables, they have the machine ID so that we can identify the machine. In the telemetry, you have a bunch of sensor readings. This is the voltage, rotation, pressure, and vibration measurements. In the error table, in addition to datetime and machine ID, you have the error ID. So you have about 5 types of error. You have 4 types of components. So in terms of failure table, you have again the datetime and the machine ID. And then you have failure of 4 components because this is a very simplified scenario where you only have 4 components. And maintenance, well, if 4 components fail, one of the 4 components gets replaced, so you also have a record of which component was replaced. Machine table is a static table, like I said. You have the machine ID, model, and age. So the goal in here is to try and get all these tables together and generate some additional features. So now feature engineering tends to be quite a tedious process sometimes, and it takes a lot of time in the entire model building process. So you essentially could have static features, rolling, tumbling features for predictive maintenance cases. So static features essentially comes from the models, the machines table, where you have the model, make of the machine, as well as years in service. In terms of the telemetry data, you could actually have the data as is, but there's always quite a bit of noise in the data. So you might want to create rolling or tumbling aggregates. So maybe if you look at voltage, you may not want to take the voltage at every hour. You could do these rolling windows where you see the, if window size is 3, W is 3, you take the last 3 data points and you could either do the mean, minimum, maximum, mode, whatever, value for that. In terms of tumbling, you see that those green windows, the window size, you see that the points, the windows are non-overlapping. So that's the difference. So rolling aggregates is something that's very commonly used. And in terms of window size, typically the domain expert would be the best to tell us what window size actually works. So you might have, if you don't have a domain expert, you might want to try different window sizes and see which feature has more of an importance. So like I said, in terms of feature engineering, the raw telemetry data is good, as shown in the table on the top, where you have daytime, machine, and the 4 sensors, which is voltage, rotation, pressure, and vibration. But, doing some amount of feature engineering actually adds to the predictive power of the machine learning algorithm. So in this case, let's assume that the domain expert kind of told us that it makes sense to look at the data at every 3 hours. So we assume that the window size of 3 is good. And if you can see in the first table, you see that all the daytime is hourly, 6 a.m., 7 a.m., 8 a.m. And then if you see in the second table is every 3 hours, 2 p.m., 5 p.m., 8 p.m., etc. So what you see is for each of the sensors, we've taken the mean and the standard deviation in this case. You could also take the range and all the other values, whatever statistic that you want to do. Okay, so like I said, finally, you want to create this massive table, which has all the feature engineers. So you have your daytime, machine ID, then all your telemetry, then you have the machine related like model, age, and then you have the failure table. So here is your final data set where you're trying to, I think we merge by machine ID and daytime as being the unique primary key in here. And the question that you're trying to answer is, what is the probability that a machine will fail in the near future due to a certain component failure? So in this case, it is a multi-class classification problem. So if you look at this table in specific, it's this machine 1, which is model. So you see machine ID is 1, and then component 1 fails. But it doesn't really make sense if I tell someone that a machine's going to fail right now, because I neither have the component nor the expertise to have someone come and replace. So the team would like you to predict a component failure at least a few hours ahead of time, a few days. So in this case, we're trying to predict component 1 failure for machine 1 at least 24 hours ahead of time. So you see that although the failure happens at 11 p.m., I go back 24 hours and I actually tag all those as impending failure. Okay, so that's how you prepare the data for the model. So once you've done all the hard work of feature engineering and creating this table, the next thing you want to do is you want to split the data into training and test. So a time-based split is ideal for this use case because the time component is used for feature engineering in terms of rolling aggregates and tumbling aggregates, and you don't want leakage of information from the training data into the testing data. So the ideal thing would be, supposing you have 1 year of data, 2020 from Jan to December. So maybe you want to take Jan to June for training. Then you want to leave a few days depending on your window size, and then maybe take from July to maybe middle of July to October, November for testing. Now, in terms of model building, there are a bunch of multi-class classifiers that are available. You could actually, we have Azure Machine Learning, which is very simple. It's drag and drop. You can click and it's very easy. In terms of metrics, it is essentially a business decision if an overall accuracy is important, or recall, precision, or F1 score. So that's all what the business would kind of help us decide. So the outline of the main steps was we first had the data, which is hourly timestamp data for telemetry for 1,000 machines per year. And then we have all this different tables of data, which is errors, maintenance, failure. And then you visualize, you build all those features, you create all those lag, rolling measures for all those sensors of telemetry, errors, etc. And then you finally build and evaluate your model. Okay, so now that we've actually gone through, so that was our traditional modeling approach, where you essentially had to look at the data, and then manually build all these features. So it is a lot of manual construction of the right features in terms of what window size do we do, what features do we keep, and etc. So it is time consuming. So this also makes these models hard to reuse. So supposing I collect one machine and it has a few sensors, in this case it was voltage, rotation, etc. But maybe the other machine doesn't have those features. So it's very hard for me to just reuse all the code that I've written for feature engineering. So this makes it hard to reuse the entire traditional model. So that is when a lot of people got to thinking, well, is there any alternate approach that we could try and use? And then over the last 5 years, there's been so much of buzz around deep learning. So deep learning has proved to be quite performant, especially in image-related scenarios like object recognition, image classification. It's also kind of gained popularity in domains where there's a lot of time series data. So now the thing about predictive maintenance also is the data is essentially time series, because you have a timestamp and you're collecting various sensor data over time. So we could try and use deep learning. So I have to say that, the attractive part of applying deep learning is that the network can automatically extract the right features from the data. So we could eliminate this entire manual feature engineering. However, the caveat is, if you have to determine the topology of the deep learning networks in terms of number of layers, nodes, hyperparameters, that is also not a trivial exercise, and you do need someone who understands deep learning and the entire architecture and etc. So let's actually think of define what a deep learning model is. So in predictive maintenance, like I said earlier, the data is collected over time to monitor the state of the asset with the goal of finding patterns. So, maybe a deep learning model would work in this scenario. So among all the deep learning networks that we have, one specific network is very good for time series data. That's called LSTM, long short-term memory network. And they're good at learning from sequences, So this is also a time series, which is like a sequence. So that's why we actually would try and see if an LSTM network works in predictive maintenance. Okay, so LSTM, like I said, is good at capturing the distribution of long-term temporal dependency in time series. So we could try and see if this works. This is how the LSTM network, each of the layers looks. So, I mean, this is the overview. We'll get into each one of the specific layers and what happens within each of these layers in more detail in the next couple of slides. So think of XT as a sensor reading at time T, and then XT plus 1 is the time after, T and then T minus 1. So you have this entire sequence of points, and all the H refers to hidden layers, HT, HT minus 1, and each one of these layers has a specific structure. So as you can see that this entire LSTM, although the manual feature engineering is taken away, and it's simplified, you have to understand the network. So I've actually given a link to a very nice blog post, which is worth reading if you're interested in learning more about an LSTM. Okay, so the core idea behind an LSTM cell is, so they have something called a cell state. So if you see that CT minus 1 to CT, so some information is going from one cell to another. So gates within the cell are ways to optionally let information through as they pass from one cell to the other. So the LSTM can remove or add information to the cell state. And then you essentially have there are three of these gates to protect and control what information gets added to the cell. So you have something called a forget gate, the input, and the output gate. So now let's get into each one of these gates and what it does. So forget, as the name suggests, the forget gate controls what is kept and forgotten from the previous state. So that's the very first thing that happens. So it essentially outputs a number between 0 and 1. So 1 represents and completely keep the information. 0 means get rid of the information. So in a more NLP related scenario, essentially is if it sees the word the cat, it will know that it's singular and it'll kind of say, well, cat which ate was full. But if it sees the plural, it'll say, well, the cats which ate were full. So if it were to predict the next word in the sentence. And obviously the mathematical equations are given and it's there in more detail in the blog post. Okay, so the next gate is the input gate. So which is essentially it decides what new information we're going to store in the cell state. And the input gate controls which part of the new cell content gets written to the cell. Then you obviously have a TANACE layer, which computes the new cell content. So the combination of these two creates an update to the state. The next gate is the output and the hidden state. So you saw a bunch of HT minus 1, HT plus 1, those are the hidden states. So the output gate, which is essentially a sigmoid layer, controls which part of the cell are output to the hidden state. So this is the hidden state, and it kind of, you try and put the cell state through a TANACE layer to push the values to be values between 0 and 1 and then multiply it through a sigmoid gate. So again, the equation is given, and if you're interested in learning more about the details. And finally, you've done all these different gate operations and you're ready to update the cell state. So erase is like forget some content from the last cell and you try and write some new content so it passes the relevant content to the next item in the sequence. It is scaled by outputs of forget and input gate. And then, essentially this cell would pick up the relevant information and pass it to the next one. So this is the recap of an LSTM cell. So you essentially have, you can forget some cell content here, write some new cell content, output some cell content to the hidden state, you compute the input, you compute the forget gate, the new cell content, and you have a bunch of these different layers stacked to create quite a dense LSTM network. So as you can see, this is not trivial, but it's kind of gained a little bit of popularity. Now, implementing this is not as complex as it looks. So essentially in Python, it's kind of easy where you can kind of define the model as being sequential and you essentially add layers. So you kind of just do model.add and you say it's an LSTM and you give the input shape, the number of units, and do you want to return the sequence or not? To prevent overfitting, you essentially can have a dropout rate of 20%. Then maybe you want to actually add a second layer. So in this case, there are only two, there's the first layer, the dropout layer, and the second layer, which is also an LSTM. Then again, you say dropout to prevent overfitting. And then you finally have a sigmoid output layer. Then you say, well, you compile it, and this is the loss I'm interested in, which is the binary cross entropy, and the optimizer I'm interested in using is Atom. The metric that I'm interested in is accuracy, and it'll kind of build the model. So you just need to ensure that your data is in the right format to input into the first layer, and then it's kind of easy to build the model in Python. Okay, so in terms of tooling and code, before we just wrap up the whole thing, is some people prefer to program in R, some prefer Python. We have, however, seen that Python is gaining more importance than R over the years, and people prefer to use Python because it's easier to operationalize the models in those production scenarios. So for R, people have a bunch of options. They could use R Studio or VS Code. It supports R and Python. And even Jupyter supports R and Python. For Python specifically, there's PyCharm, a bunch of different tools that you could use. And here's some sample code for R that you could run in a Jupyter notebook, as well as this is some code in Python where you can run this code in Jupyter notebook, as well as these are some links to kind of get you started on reading about connected factory, industrial automation, predictive maintenance, and then we have an AI guide for predictive maintenance, and this is the blog that I told you about, understanding LSTM models. So, yep, so that is all I had. So we have about 9 to 10 minutes, and I'm open to questions if there's anything.
Great, thanks a bunch, Jaya. I don't see any questions yet, but if anyone has any questions, please feel free to add them into the chat or the Q&A box, and Jaya can take them up. We'll give folks a couple minutes.
Yeah, thank you.
Okay, well, it looks like no one has any questions for Jaya now, but if you do have them later, you can always feel free to reach out to her on Twitter. I think, Jaya, you linked your Twitter there.
Yes, I did.
Yes, so that's great. Oh, I just saw one come in. Oh, there you go. Well, while you're answering that question, I just posted the link to a survey for today's session, and if you had any feedback, we'd love to know how to make things better, or if things are great, we'd love to know that things are great and to keep doing things the way that they're going. Yeah, so just any feedback is all good feedback for us. So if you wanted, and if you had a couple minutes, it should only take about 30 seconds to a minute. If you could take the survey, that always helps. And beyond that, Jay, I think there's a question in the chat that you can answer.
Ah, okay. What is the question? So.
Oh yeah, sorry. The question is, do people take into account / model for sensors themselves deteriorating over time?
Model for just a sensor as opposed to the entire equipment. I think that's what it is.
Yeah, I think so. So do people take into account that those sensors deteriorate over time?
Well, that is an interesting thing, actually. So we are assuming that, so then you'll have to build a predictive maintenance model for the sensor as is, isn't it? So actually, I think most of our cases, what happened is the machines were not even instrumented. So we actually had new sensors put in there. So we're assuming that those sensors were high quality and didn't have any issues. But yeah, that is an interesting thing. So we haven't actually addressed that. Yeah.
Okay. Jaya, while you're answering questions, could you put your last slide with your Twitter on there back up on the screen?
Yep. Yep,
okay,
I can.
Perfect. Awesome. And then while you're doing that, there's one more question. They asked, are there any standard LSTM models that can be used as a starting point?
Well, so I think the example notebook that we have in here is a good starting point. So I think that, I don't know how many layers it has. Now I haven't looked at it, but I think that is the one that you want to look at. So there's a deep learning one. So I actually know more of standard models for custom vision and NLP, but predictive maintenance, no. Not really.
Okay, perfect. I think we have time for one more question if folks have any. But if not, we can wrap up a little bit early and give folks like 4 minutes back of their time. All right, yeah, I don't see any coming in. So thanks so much, Jaya. Thank you so much for your time. For those that are on the call, the recording for this session will go up on our YouTube in about 2 days. And if Jaya agrees, we'll also share her slides in the description, so you can just reach out there. I know there was a question about that. And thank you so much for joining us. Thanks, Jaya.
Thank you very much.